Hello everyone. Welcome to the third lesson in our journey of learning calculus. This course is designed to guide you step by step through the fundamental concepts of calculus, building your knowledge from the ground up. My name is Shaunak and you are watching this video on my channel Physics for Students. Welcome to the third lesson in learning calculus. Now, as we continue our learning to know functions, as I have done in the previous two lessons, these are the building blocks for calculus. We will start today with certain other functions, and first we would start with what are called polynomial functions. Now, if I go by the definition, a polynomial function is basically a kind of a mathematical expression which consists of certain terms which are made of constants as well as variables, and they are raised to certain whole numbers which are called exponents, and it takes the general form of this. Now this is how a polynomial looks like. Now why it is -1 at the base and why it is -1 at the exponent, these things I am going to explain to you later. But first, when we understand any term or any mathematical concept, we understand by its definition. So what do we mean by poly? So it is again taken from the Greek word poly, which means many, and nomial, which means term. Together it says many terms. And as you can see in the expression, mathematical expression, it actually consists of many terms. So we can say that the degree of the polynomial or the power which has been raised to actually determines the function's general shape and behavior. What do we mean by general shape and behavior? We will explore it one by one. But here you can see this, what I was telling you, a sub n minus 1 dot 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 up to a0. These are called constants. I mean to say they are basically coefficients. And n is basically a non-negative integer. That means it cannot be a negative. That indicates the degree of the polynomial. So this is an overall idea of the definition and how the mathematical equation looks like. Now, in order to explain a little bit more about the polynomial, what they are actually, I'm to say if you go a little bit more in understanding the equation, then let us take this term, and now we will try to decipher the equation one by one. So at the top, what you can see, this is the exponent, which you can call as the power. 5 is basically the coefficient, t, or it can be anything. It is called a variable. You get either a plus or a minus or whatever. These are, as you know, are operators. M is again a variable. Minus is again an operator, and 2 is basically a coefficient, and 20 or what comes after the operator is basically a constant. So this is overall the structure, you can say the skeleton of an exponential function or an exponential equation. Now there are different types of polynomials which will again come very useful when we are doing differential or integral calculus. But before that, I would like to give you certain definitions and a graphical understanding of what these are, because we will take those polynomial in future when we are learning differential calculus and integral calculus. So the first is called a constant polynomial. That means a polynomial which has degree 0. That means it has no power, and it looks like this. f of x equals to 7 or f of x equal to -3. So this is called a constant polynomial which has got no degree. The second one is called a linear polynomial. So linear polynomial, because it is linear, that means it will have a straight kind of a straight line. So it will have a degree 1, and it has the form ax plus b, and where a obviously will not be equal to 0. And the example is f of x equal to 2x plus 3 and f of x equal to minus x plus 5. So you can think of a straight line with a slope a. The second is called a quadratic polynomial, and the definition is that it will take the form of ax squared plus bx plus c. As you can readily see that the power is of 2, and the example is again this. So you can see a parabola, which we will see later, coming up or down depending upon the signature or the sign of a. So this is called a quadratic polynomial. Next comes what is called a cubic polynomial. So you see from starting from linear, which had got a degree 0, then quadratic, which has got 1, and the cubic, which has 3, and it takes this form: ax cube plus bx squared squared plus cx plus d. Again, a should be not equal to 0, and this looks like this. So a cubic polynomial is mostly like a S-shaped curve that may have 1 or 2 turns depending on the roots. We are also going to see the graphical description of that. The next one which is called a quartic polynomial. Quartic means 4, so it will obviously take this form: ax4 plus bx cube plus cx square. But the primary, the first part would be 4, and this would be looking like this: f of x equal to x4 minus 6x squared, and so on. So quartic polynomial, as we will see, will take the shape of a w or an m depending upon the I would say the sign and the number of real roots. Next comes this is not really much used in terms of real life application, but still it is very important. It is called a quintic polynomial. So it has a degree 5, and it takes this shape: ax5 plus bx4, and so on. And it would be, the example would be where a x not equal to 0 and f of x equal to x to the power 5, etc. Now this graph is with a up to 4 turns because it has got quintic polynomial of 5. So you can see a complex curve with up to 4 terms could have different types of shape, again depending upon the coefficients. Now apart from that, the terms that describe the number of terms in the polynomial are monomial, that means a polynomial with just 1 term; binomial, a polynomial with 2 terms; and trinomial, a polynomial with 3 terms. So these are more or less what we called are the different types of polynomials, examples, and we will see how they look like in terms of the graph. Now, as we talk of linear functions, we first talked about what? Number 1, if you go back to the video, you will see it was called a linear polynomial. So let us see what is a linear polynomial, what would be a linear function. So this statement means that the linear functions, for example, f of x equal to mx plus b, where m is not equal to 0, will have polynomial of degree 1. Here you can see f of x equal to mx plus b. This is a linear function which has this form. Here if I go one by one, you will see m is basically the slope of the line, that means how steep it is. And if I go by b, this is the y-intercept, that means the value of f of x when x is equal to 0. And this is how things happen. I meant to say this is how the equation has been arranged. Now the degree of a polynomial, as you know, is the highest power, or you can say technically exponent, of the variable x with a non-zero coefficient in a linear function. In a linear function, the term mx has x raised to the power 1, which means, as I'm not mentioned, that means it has a polynomial of degree 1. So if m is not equal to 0, and the x term is present, if the x term is present, and the function is indeed of degree 1, however, if m is equal to 0, the function becomes f of x equals to b, which is a constant function, and it has got a polynomial of degree 0. So from here, what we can understand is that a linear function with m not equals to 0 is called a polynomial of degree 1. Because it contains an x term raised to the first power and has a non-zero coefficient m. So this is what is a linear function, the exponent, and what does it mean. Now, as I have been telling that these are all mathematical equations, but how about showing them into nice graphs? I mean to say pictorial description. So now in the next part of this video, we will understand graphs of polynomial functions and how do they look like. So first what I'm going to do is that I'm going to take a function, an equation, something like this: y equals to x cube upon 3 minus x squared 2 minus 2x plus 1 upon 3. And this would show this kind of a graph. And we are going to analyze this graph one by one so that we can understand the polynomial function and the graph that it produces. Now, as you see that the function of degree 3 is leading with a term 1 upon 3 x cube, or x cube by 3. So obviously it takes like a snake-like form, and we call it as an S-shaped. More or less, it is something which looks like an S-shaped. So from here, as you can see, this x cube upon 3, this is actually what it shows, that it is a cubic term, a polynomial of cubic. So as you see that a cubic function can have up to 2 terms. Here you can see 1 and 2. There are 2 terms, and this creates the similar S curve or a snake-like form. Now if I want to understand that x cubed by 3, which I was telling, and if I take this part, then what we can see as the leading term, leading means the first term of the equation, then the positive coefficient of x cube indicates that x tends to infinity and also y would tend to infinity. And if x is going towards minus infinity, y would also go towards minus infinity, and this opposite behavior gives the overall graph the shape of an S. Now in order to, so here is what is called the local maxima, and this is what is called the local minima. Although I would like to draw attention, this is a wrong way of determining maximum and maxima and minima. We have to take the derivative and so on. Once we learn how to take a derivative, we will definitely again revisit calculating maxima and minima, but this is just a kind of an intuitive understanding of how this graph looks like. Now if we are taking the y-intercept, that how it intercepts y, so obviously we set x equal to 0, and this is the equation which goes through. So from here what we can understand is that the y-axis intercepts at 0, 1 upon 3. So you can see more or less in this graph this is how it looks like. So from here we move to the next kind of a graph which gives another kind of a polynomial equation. And here you can see this is a quartic polynomial equation because it has given the highest power of 4. And we will analyze and see how the graph characteristics look like. Now because this is a degree of 4 polynomial with the leading term at 8x to the raised to the power 4. Since the leading term 8x4 has a positive coefficient, so the behavior of the graph will be y equal to 8x4 kind of a thing. So here also as x goes towards infinity, y will be positive, and x goes towards negative infinity, y would be negative. So what does it mean? That the both ends of the graph, as you can see here, will rise upwards, typically for even degree polynomials with positive leading coefficients. So if the coefficient is a positive leading coefficient, the graph will, as you can see on the left hand side, it has rose upwards, and the right hand side also in the x-axis it has gone upward. So so here you can see, first of all we will calculate the intercept, but what I would like to say is that a quartic polynomial function can have up to 3 points, that means local maxima and minima. So, so if I take say for example setting x equals to 0, from here what we can get is this kind of a thing where we get the value as -1. So a quartic polynomial function can have up to 3 turning points, local maxima and minima. Here you can see this is the minima, and this is again it is intercepting at -1. This is at this point, this is almost at between 0 and 1. And this is again the minima, and this is at point number 2. So as I was telling right at the beginning when we were learning the definitions, that a quartic polynomial will take a shape of a W or an M. So here you can see it has taken a shape of a W. So the most important thing is that no particular symmetry actually is this, as a function has a mix of even and odd powers. You can see the polynomial function, it has got 8x to the power 4, then 14x to the power 3, then nx to the power squared. So 4, 3, 2, 1. So obviously there is no symmetry, and the function has a mix of even and odd powers. And from here what I was telling just a few seconds earlier, since the function has a positive leading coefficient, these turning points will create a W or a M shape, and the graph has 2 valleys and 1 peak, and 2 peaks and 1 valley. So what we can deduce from here is that quartic functions do not have an inherent symmetry like even or odd symmetry, unless they are specifically designed to be even functions where all the powers of x, or odd functions all odd powers of x. Here the function has both even and odd powers, so there is no specific symmetry. And because the degree is even and the leading coefficient is positive, both ends of the graphs will move upwards towards positive infinity and negative infinity. Let us look into another kind of equation, and how does it show. So this is another equation, and this shows a graph something like this. Now here you would see what we have seen, that the degree of the polynomial, if you add up the degree of the polynomial, it would sum up to 8. And what does it mean? It means that it is a polynomial of degree 8. Since the degree is even, just like the earlier, the graph will have the same behavior at both ends. So the left hand side goes up to infinity, right hand side also goes up to infinity. So x goes towards infinity, x goes to minus infinity, y towards positive infinity and negative infinity. Now roots, how can we calculate the roots, intercepts and multiplicities? So from here what we can see, if x equals to 2, it has got a with multiplicity of 4, then it is around here 1, 2, 3, round about, somewhere around this position. If it equals to minus 1 with a multiplicity of 3, so it would have this part. So x is positive 2, this one, x is negative 1, this one. And if x equals to 1, it has got a multiplicity of 1, so it would be around this point. So what we get is that if x is equal to 2, multiplicity of 4, the graph touches the x-axis at x equals to 2 and turns around without crossing it, even multiplicity. X equals to minus 1, multiplicity 3, the graph crosses the x-axis at x equals to minus 1, the left hand side, with a flattening effect near the root. Why? Because odd multiplicity greater than 1. And if you see the last one, x equals to 1 with multiplicity 1, the graph crosses the x-axis at 1 and makes a sharp turn. That is, it has got an odd multiplicity. So this is, I mean to say, there can be numerous other examples, but this actually gives us an understanding of how the graphs in polynomial, the quartic, the cubic, etc. looks like, and how they behave with positive and negative infinity. So this one is 16, so this is how it behaves. So we come to the next part of our video, where we will quickly look into another important function, which are called rational functions. Now these are extremely useful in daily life. So how does a rational function looks like? It looks like this, where this p of x and q of x are polynomials, where obviously q of x should not be equal to 0. Some examples are this, this and this. Now, if I talk of the rational functions usage, yes, it is important for modeling real life phenomena. So rational functions appears in context where one quantity depends in another in a way that involves division of proportion. For example, speed as a function of time or distance. The second one is what is called understanding of physics and engineering. Yes, in physics and engineering, it becomes extremely important and it has been used. Economics and I would say science. Yes, it is very much used in economics in calculating the trends and finance, etc. And also it has been used in medicine and biology in different ways when we used to calculate the functions where one depends on the other. Now, once we understood what is a rational function, let us look into the graphs of rational functions so that we can really understand how the graph, etc. looks like. So in this part, we will take an example of this, y equals to 2x squared minus 3. This is a rational function, as we have seen. And the graph would be looking something like this. Now, just note that this is actually a quadratic function, which typically forms what is called a parabola, and you can identify from the right hand side what is a parabola. But what is very important is this one, 2. Okay, since 2 is important. Why? Because the coefficient of the x squared, that means the 2, is positive, and that means that the parabola opens upwards. The vertex of the parabola is at 0, minus 3. So here you can see the parabola open upwards. So if I take the degree of the numerator, as you can see, is 2, and the degree of the denominator has got nothing, that means it is equals to 1. So if I take the degree of the numerator as 2 and the degree of the denominator as 1, since the degree of the numerator that is 2 is greater than the denominator, which has nothing, that means 1, no horizontal asymptote exists. This is important. Instead, there will be a oblique or a slant asymptote, and this animation shows this one, this it goes. So the red line, I mean to say the red line, I've just draw it parallel to that so that you can understand. So because the degree of, now you might ask a question, is it that always the degree, if the degree of the numerator is greater than the degree of the numerator, it will have a oblique slant asymptote? No, in the later video I will show you there might be exceptions to that. So this is how the asymptote looks like. It has got a slant asymptote. So if I now want to calculate, for example, if I perform a long division of 2x squared x cubed minus 3, 2x squared minus 3 by 7x plus 4, then what we get is this kind of a graph where you can see that the graph approaches the oblique asymptote. And near x equals to minus 4 upon 7, the denominator actually approaches 0, which means that causing the function tends towards plus minus infinity depending on which direction you will approach. So here again, as x approaches this, y approaches this, and x approaches this, y approaches negative infinity. So here it is, to find the horizontal asymptote, we can compare the degrees of that. So the degree of the numerator 2 and 1. So it would have somehow reached upon this place, and here it is upon this place. So it is plus 4 as on the numerator, and x is negative 4 when it is negative infinity. So it is right at the in the lower end of the axis. So this is how it looks like. So with this equation again, we get this kind of a graph. So these are all, rational functions. I'm just trying to show you different examples so that things become clear. Now here what happens, since the degree of the numerator that is squared and denominator are equal. So 5x squared and 3x squared. So the numerator and denominator, the degrees are equal. There is a horizontal asymptote, and the ratio of leading coefficients equals to y equals to leading coefficient of the numerator 5 upon 3. So thus x approaches plus minus infinity, y goes towards 5 upon 3. So this is another example. When you get a degree of the numerator and the denominator are the same, you won't get a kind of a slant. It will get a horizontal asymptote. And if I want to calculate the y-intercept, I will obviously have to take x equals to 0. This would lead to this kind of an equation, and the y-intercept would be here 0 comma minus 3 upon 2. So here, as you can see, as x approaches plus minus infinity, the graph approaches horizontal asymptote where y equals to 5 upon 3. Let us see another example of rational function, this one. Here the function has got a vertical asymptote. Yes, here you can see it is. And the same rule applies. The function has got a vertical asymptote where the denominator is 0. So as x is this one, and as this goes towards, y goes towards positive infinity, and x is this one, it goes towards negative infinity. Y goes towards negative infinity. This is the cube roots. Now the degree of the denominator 3 is higher than the degree of the numerator, which is 1. So obviously x would be plus minus infinity and y would be towards 0, and there is a horizontal asymptote where y equals to 0. And if you want to calculate x intercept, then we have to set this equation, which will be minus 2 upon 11, and the x intercept is minus 2 upon 11, 0. To calculate the y-intercept, we do the same kind of an equation. Just calculate and substitute the values. We get the y-intercept as 0 comma minus 2. So this is how the rational functions are, the different behaviors, etc. We move on to the next type of a function, which are called algebraic functions. And these are quite simple because they have a kind of a formula. So an algebraic function is defined by a polynomial of equation in x comma y. Now these functions can include roots, powers, and basic arithmetic operations as we do, and this takes the form of this, where this p of xy is actually the polynomials in x and y. If I solve explicitly, this would lead to this and this and this. Now there are different types of algebraic functions, for example polynomial functions, etc. So I would just first like to show you a graph, and I will take this function y equals to x upon 1 upon 3 x minus 4 and to find the x intercept, what I'm going to do is that I'm going to solve it. So solving x upon 3 equals to 0, what we get is x equal to 0 or x equals to 4, which brings us at this point and this point. Now, in order to find the y-intercept, what we will do is that we will set x equals to 0, and that would be y equals to this, and the y-intercept would be 0, 0. And you can see already that is there. So the end behavior of this curve is that as x approaches positive infinity, x upon x to the power 1 upon 3 grows positively, and x minus 4 also grows positively, so y goes towards positive infinity. As x goes towards negative infinity, x minus 4 also goes negatively, and we get y which is going negatively. So this is a kind of an, so let us see another example of algebraic function, how it looks like. You will be clear. So with this we get a kind of a graph like this, and you can already see that to find the intercept we take y equals to 0, and we get this value which gives x equals to plus minus 1. So here it is x intercepts a minus 1 0 and 1 0. So here is 1 minus 1 0 and 0 positive 1 comma 0. And if I substitute minus x for x, that means I'm just taking the value of minus x and substituting for x, I get a value of this. And this means that the function is even and the graph is symmetric about the x-axis. The graph is symmetric about this y-axis. Similar kind of a thing we can find out about this kind of a graph. And if you want to really do a little bit of mathematics, do let me know in the comment box that how this graph it looks like and what is the y-intercept, x-intercept, and so on. Now we come to the last part of our video, which we will just touch base because you already know this, and these are called exponential functions, which are extremely useful in calculating populations, etc., and a lot of other practical usage. So what is an exponential function? We take f of x is equals to a to the power x. That means the exponent, where obviously the base a should be greater than 0 and a is not equal to 1. Otherwise, how it can be an exponential? These are called exponential functions, and all exponential functions have a domain from minus infinity to positive infinity, and the range should be 0 to infinity. So for example, if I take y equals to 10 to the power x, the graph would look something like this. Again, you can see there is an asymptote. So if I again try to calculate the y-intercept, I would take this and the graph passes through 0, 1. Y equals to 0, that means it has got an asymptote, and x is going towards negative infinity, y towards 0, and remember the graph never reaches y equal to 0. So what happens is that the graph grows and grows and grows extremely rapidly at x tending towards infinity with a y equals to 10 upon x. So that is why it has got an asymptote. Now this type of an increase is basically tenfold for every unit of increase of x. So this type of graph are very useful. For example, as I was telling, population growth, compound interest, amplification electronics, and various other reasons. So we will take a pause right now, and we are almost done with our knowledge of different type of functions, graphs, etc. And in the next part of the video, we will be exploring more and moving towards the real problems and understanding of calculus. Thank you very much for those who have taken time to watch this video. If you have liked the video, please do not forget to subscribe to my channel, Physics for Students, and click on the bell icon to get all the notification from Physics for Students. You can contact me at this email ID, and you can also subscribe to my other channel where I have already put up almost 4 or 5 videos on general relativity, and you can follow me on my Facebook, LinkedIn, and Instagram account. Thank you very much for watching this video. Stay tuned because this calculus series is just started and we're still going on with some real good news on podcasts coming up by the end of this one. Thank you very much.